So let's talk about what a radian is. So here's a circle. So we said a radian had to do, as the name suggests, with the radius. That's true. So what I'm going to do, I have this little strip of tape, and I happen to have already cut it to exactly the length of the radius of this circle. Okay? So the length of this tape is the radius of the circle, R, we'll call it. So, what I'm going to do is take the length of this radius, and I'm going to wrap the length of the radius around the outer edge of the circle, like so. Now it curves, so I want to curve it, push on it with my fingers, and this isn't an exact measurement because I'm using a little slice of tape, but I'm going to get a pretty good estimate. I make it about that far. Okay? So this length right here is also the radius of the circle. It's just wrapped around the outer edge of the circle instead of from the center to the edge, like so. So it's the same length right there. And when I do that, when I wrap the radius around the edge of the circle, I make an angle. I can think about this as a certain amount of rotation. Okay? And I call this amount of rotation a radian. So this amount of rotation is 1 radian. And that is the amount of rotation you get when you wrap the radius around the outer edge of the circle. So I take the radius length, wrap it around the outside. That takes me a certain amount around the circle, and I call that 1 radian. Now, if I had a tiny circle like this, with a tiny radius, do you think it would be a smaller angle, a bigger angle? Well, what does your gut tell you? Yeah, so there's not as far to go around the edge of the circle, right? But the radius is also smaller. So it turns out it works out exactly the same. 1 radius, 1 radian is 1 radian. It doesn't matter how big the circle is that you use. It's always the same amount of rotation. Okay? It's a shorter distance here, but you rotate around the circle by the same amount. So that's what a radian is. And because it works for every circle, it's not arbitrary. It's not something that somebody decided to use, like a degree, for convenience. It is a property of a circle, and that makes it more convenient to use for some higher mathematical things in physics that we'll talk about a little bit later. So, question. About, let's estimate, about how many radians do you think it'll take to get, let's say, halfway around the circle? So just halfway around the circle first. About how far do you think it'll be? Just eyeball it first. 3? About 3? A little bit more, a little bit less? Or exactly 3? Okay, let's find out. So there's 1. This is an inexact measurement, but it'll work for now. There's 2. So there's 1 radian. So this would be 2 radians. That's 2 radiuses wrapped around the circle. And then 3. That's 3 radians wrapped around the circle. So half of a circle is a little bit more than 3, right? Okay. And that means it's going to be about how far to make an entire circle. Yeah, about twice as far. Oh, we can measure from the right. There, and then about there, and then about there. So there's 4 radians, 5, and 6 radians. So it's a little bit more than 6, right? So what's a popular number that has to do with circles that's a little bit more than 3? Pi. Hey, guess what? Exactly how many radians does it take to get halfway around the circle? It takes exactly pi. Or approximately 3.14, etc., etc., etc. Which means it takes exactly how many copies of the radius to make it all the way around the circle once. Hint, it's twice as much. Yeah, 2 pi. Or approximately 6.28. And maybe that makes sense. Does anybody off the top of their head remember the formula for the circumference of a circle? In other words, the total length of the outer edge. I'm going to pretend you didn't say that last thing. Yeah, it's 2 pi r. It's 2 pi times the length of the radius. That's the complete outer edge of the circle. Right? Okay. So in other words, it takes 2 pi lengths of the radius to make one complete circle. One trip all the way around the circle. It doesn't matter how big the circle is. It's that same amount of radians, of radius lengths. Okay. So I'm going to sketch this right here. So we take the radius, we wrap it around the circle like that. It makes an angle, and that angle is 1 radian. And the full circle is exactly 2 pi radians. And what you can remember, something that you should already remember, is that to make it completely around the outer edge of the circle, also known as the circumference, it takes 2 pi radians. So there we go. So something you should already know that can help you remember this value right here. All right. And I'm just going to draw a picture here. To help you remember. So 360 degrees is 2 pi radians. That's a full circle. How many degrees is half of a circle? Hint, it's half of 360. 180. So 180 degrees equals, and what would half of a circle be in radians? Yeah, a little bit more than 3. 1 pi, exactly. Okay. So one thing I want to point out here. Notice that I don't write any units when I write the radian value. That's because we're just counting things. So when we use degrees and we write down that measurement, we have to say what we were counting by. But for radians, we're just counting lengths of the radius. So you count 1, 2, 3, 3.14, etc. So it is exactly pi radian. So we don't write units here. And for this reason, this becomes very convenient to use for mathematical calculations. How many of y'all are in or have taken physics? Most of you? I'll probably ask this question again. So have y'all talked about Kelvin? A way to measure temperature? So Kelvin turns out to be nice for measuring temperature, because instead of 0 being some arbitrarily chosen value like it is in Fahrenheit and Celsius, 0 is actually 0. Right? 0 is a property of the universe that's absolute zero, and you base your calculations off of Kelvin instead of Celsius, because Kelvin relates directly to the universe, whereas Celsius involves some sort of conversion. It's the same with radians. A radian is based off of a property of the universe. In the universe that we exist in, on a flat plane, if you make a circle, it will always take 2 pi radians to get around that circle. It doesn't matter where you are or how big your circle is, whereas a degree is based off of an arbitrary choice. So for that reason, it's more convenient to use radians in mathematical calculations, unless you're like looking at a triangle or something. But it's more convenient to use radians in general than it is to use degrees, because we don't have to worry about the units that we're measuring in, because it does not have units in the same sense, because it is not arbitrary. Okay. So what we want to do first is to have an intuitive sense of how big, say, a 73-degree angle is, and about what that would be in radians. So to start off, I'm going to draw a circle. This is a special circle drawing tool. You likely have one on your desk already. If not, there's a big box of them back there. Feel free to grab one. You will not want to do that. You'll also want a case, because the case is going to make a handy straight edge. Okay, so I'm going to start by marking the center of the circle. Then I'm going to trace around the outer edge. Don't forget to mark the center, because that's an important part of the circle. Okay, so I drew a circle with a dot in the middle. Everybody with me so far? I'll give you a second to catch up. Okay. So what we're going to do is we're going to take this circle and we're going to cut it up into pieces. The first way I'm going to slice this is straight across horizontally. And you can use your convenient circle drawing tool carrying case as a straight edge here. It's almost exactly the right length. Okay, so we cut this horizontally. Now, when we think about rotation, you've got to start facing a certain direction. Okay? And so what we're going to do here is start just by picking a direction, a starting direction, and it is conventional to choose this direction, so the right, east, to choose that as your starting direction. So we're going to choose this point to represent 0 degrees, which also happens to be 0 radians. It's the same spot. That is no rotation, no matter how you're doing it. So we're going to start from no rotation. It's also convenient for us each time to rotate the same direction. And how do we denote directions for rotation? We say like left and right. Yeah, clockwise and counterclockwise, and we will call those positive and negative. So our positive direction is going to be counterclockwise. So in other words, not the way a clock goes, the other way. Counterclockwise, that's our positive direction. So we're going to rotate this way. And if we happen to rotate the other way, that's going to be the negative direction. And we'll talk about that more later. So for now, we're going to take a little journey around the circle, and we're going to hit some of the highlights along the way. So the first highlight would be Not the first one we cross, but the first one we're going to talk about. The most important one is going to be halfway around the circle. So, how many degrees would be halfway around the circle? How many degrees of rotation? 180 degrees. And I'm going to leave that there, and we're going to come back and talk about the radians after we set up all of our signposts in degrees. Okay. So half of a circle is 180 degrees. What if I make an entire circle's worth of rotation? Yeah, that's 360 degrees. So for 360 degrees, I end up in the same spot I was at 0 degrees. That's one complete circle. And of course, I could continue spinning over and over again, but let's just start with one circle for now. Okay, so this point right here is either 0 or 360, depending on whether you spun. Now, let's cut this in half again. So I'm taking the circle, I'm slicing it in half again, and so let's look at these endpoints. Each of these is going to represent a certain amount of rotation. So from 0, how far do I have to rotate to get to the vertical position right here? Yeah, that's 90 degrees. So this angle would be 90 degrees. And how far would I have to rotate to get to this? So there's 90. There's another 90 to get to 180. And then there's another 90 to go straight down. What angle would that be? Yeah, that's 270 degrees of rotation. So if we're looking at this, at these lines, each one is 90 degrees, so you just count by 90. 90, 180, 270, and then if I rotate another 90 degrees, I get to 360. Okay? So let's put radian counterparts with these. So 180 degrees, half a circle. We said that's how many radians? But exactly pi, yeah. So we're going to use exact numbers here first. So that is exactly pi radians. So pi, in this case, isn't round like a lot of pies that you might have seen. In this case, pi is more like a calzone. It's folded in half, or a fried pie, however you want to think about it. So pi is half of a circle. Okay? If you bring it, then yes. Yes. And because there are 30 of us, it can be easily divided between 30 people. Okay. So let's look back up here. Alright. So I want to figure out how many radians this is. And to think about that, I'm going to think about pi. Not the delicious kind, but the mathematically useful kind. So pi is half of a circle. So then what fraction of pi is this first angle going to be? Yeah, it's halfway there, right? It's halfway to a calzone. So we're going to write this as half of pi. Or in other words, pi divided by 2. Right? That's half of pi. Okay, so there's 1/2 of pi. If I add another half, that's 2/2 of pi, or in other words, an entire pi, a calzone in this case. Now I'm going to add another half pi. So to get from 180 to 270 in radians, that's going from pi and adding another half pi. So how many pi's is that? Yeah, it's 1/2 pi, right? Or 3/2. That's 1/2. And when we write these fractions, usually we're going to write the pi on the top. You could write it off to the side too, but it's going to be more convenient to write the pi on top. So 3pi/2. That's 1/2 pi. And then if I add another half pi, so there's 1/2, 2/2, 3/2. This is 4/2 of a pi. Or in other words, it's 2 pi. Just as we predicted. Okay. So, when we're looking for angles these are going to be our first signposts that we use. If I want to find the angle, let's say 220 degrees, which quadrant would 220 degrees be in? Would it be in the first quadrant? No, it's not between 0 and 90, is it? 220, is that between 90 and 180? No. Is it between 180 and 270? Yes. So I know which quadrant to look in. So that's going to be an important first step here. These numbers help us narrow down to a quadrant when we're looking for a certain angle. Now, we can actually narrow this down a little bit more. And to do that, we're going to cut each of these quadrants in half. And we're just going to eyeball it here. That looks like half. And that looks like half. Okay. So let's do degrees first. I'll give you a second to slice your pie. Okay, so let's look at just the first quadrants. So the first quadrant was 90 degrees, but then I cut it in half. So what's half of 90 degrees? 45. So this first rotation I make is going to be 45 degrees. And then I'm going to keep rotating around by 45 degrees. So another 45 would be 90. And then another 45 would be 135. So we just keep adding 45 degrees each time as we go around. So 135 plus 45 is 180. I already have that one. And then we add another 45 degrees for the next rotation, 225. Then we add another 45 degrees, 270. Already got that one. Then we add another 45 degrees, 315. And then we add another 45 degrees, and we get 316, just like we were supposed to. So we know we probably added right. Okay, so these angles are going to be important to know too. So in that previous example I said, hey, about where would 220 degrees be? Well, first we can narrow it down to a quadrant. 220 degrees would be somewhere in the third quadrant. And if we know where the middle of the quadrant is, 225, we can figure out which side of the quadrant it's on. So is it closer to 180 or closer to 270? 220 degrees, that is. Yeah, 220 would be closer to 180. So it's going to be in this half instead of in this half. So by knowing these angle signposts, these important angle values, that allows us to find angles without having to do a lot of math in our heads. We just know some of these, then we can narrow down our choices, and we can find whatever angle we want to find. Let's try to do the same thing with radians. So we started at this angle right here. It was 45 degrees. Let's think about that in terms of pi. So again, pi is half of a circle. And when we write this, we're going to write this as a fraction of pi. So what fraction of pi would this rotation be right here? Yeah, it's 1/4 of pi. If we put 4 of them together, we get pi. So this is 1/4 of pi. We're going to write this as pi over 4. And instead of adding 45 each time as we go around, we're going to add 1/4 every time we go around. So I'm going to put a box around this one. This is what we're going to count by when we draw these. So I'm counting by fourths of pi. So there's 1/4. So 1 out of 4. And if I add another one, I get 2 out of 4. Which is 1/2 of pi, right? And if I add another fourth, I get 3 out of 4. So this angle right here in radians is 3 out of 4 pi. And then the next angle, I add another fourth, that's 4 out of 4, which is, of course, just 1. So that's 1 pi, 4/4 of pi. Then I add another fourth, that's going to be 5/4 of pi. 5 out of 4. Then I add another one, and that's 6 out of 4, which of course reduces to 3 out of 2. And then I add another one, and that's 7 out of 4. So that's going to be my angle in radians over here. And then I add another one, and that's 8 out of 4. And 8 out of 4 reduces to 2. Okay, so in that way, just counting by fourths, I can figure out how many radians each angle is going to be. All of these important angles that I'm going to have to deal with a lot. So, if I wanted to know how big, if I wanted to convert the angle 225 degrees into radians so that I could use it in some sort of mathematical equation, I could write down a unit conversion, but I could also just count. So if I know where 225 degrees is, I can just count by fourths. So that's 1, 2, 3, 4, 5 fourths of pi. So this makes it really easy to find angles both in degrees and in radians. All you have to do is count. And we can all count? Yes? Most of us? Okay. Cool. If not, we'll work on it. We'll get a lot of practice. Okay. So, quick example. Let's say I wanted to draw, so I want to roughly estimate where 300 degrees is. Okay, so I want to know about how much rotation is 300 degrees. So I'm going to draw it. This is the kind of thing I'm going to have you do on the homework. So first I'm going to draw a circle. And I'm always going to start from 0, and I'm always going to go, unless it's negative, I'm going to go counterclockwise. So 300 degrees. I'm going to start by drawing this crosshair. These are my 90-degree angles. So I've got 90 there, 180, then 270, and 360 would make a full circle. So which of those numbers is 300 between? Yeah, it's between 270 and 360. So it's going to be in this quadrant right here, the fourth quadrant. And is it closer to 360 or is it closer to 270? It's closer to 270. So 300 degrees is about there. Okay, so this is the level of accuracy we want to have just from our intuition. Hey, about where is 300 degrees? Well, it's going to be in the fourth quadrant, closer to the bottom. Okay? And having this picture is going to help us do that. Similarly, what if I wanted to draw let's say 5 pi over 8. A fraction. Okay. So let's see if we can get this in the right quadrant. So I've still got 0 here, but for radians I've got halves of pi. So there's 1/2, there's pi, there's 3 pi over 2. So which of these two numbers would 5 pi over 8 be in between? Is it between 0 and 1/2? So is this bigger than 1/2 or smaller than 1/2? Bigger. So what I'm going to do when I draw this is instead of writing pi over 2, let's think about that in eighths. How many eighths would half a pi be? That would be 4 eighths, right? And how many eighths would an entire pi be? 8 eighths. And how many eighths would 1.5 pies be? 12. Okay, now it makes it really easy to tell which quadrant this is going to be in. So 5 eighths, would that be between? That would be between 4 and 8, right? Between 4 eighths, which is half pi, and between 8 eighths, which is 1 pi. And is it closer to 4 or to 8? It's closer to 4. So it's somewhere around there. So 5 eighths is going to be that much rotation. 300 degrees would be that much rotation. So that's what we're looking for on a problem like this. We want to know roughly where that angle is. Okay? And we'll get lots of practice doing that. But first, let's talk about some other important angles that show up. So these are the 45-degree angles. Those are important. Some other angles that come up a lot are not multiples of 45 like those, but multiples of 30. So I'm going to make some space on the next page and make another big circle. And we're going to try and slice this up into 30-degree angles. Now, how many 30-degree angles could we fit into a 360-degree circle? Yeah, 12 of them. So really what we're doing here is we're drawing, what's another circle that's cut into 12 pieces? Hint, there's one on the wall. A clock. So basically what we're doing here is we're drawing a clock. So I'm going to start by drawing a horizontal line here. So this is my 0 degrees and my 180 degrees, also known as pi, also known as 0 radians. And I'm going to go ahead and draw my vertical line here too, because that shows up on the clock. So this would be like, I'm going to write the times in here. So this is 12 o'clock. And which hour is directly to the right? Yeah, that's 3 o'clock, right? And then 6 o'clock is straight down. And which one is directly to the left? You're right, it's 9 o'clock. Okay. So to cut this into 12ths, I'm not going to cut each of these quadrants in half like I did before. That would be 1/30. But I need to cut each of these quadrants into how many pieces? Yeah, I need to cut it into 3 pieces. So there are 2 numbers in between 3 and 6, right? 2 whole numbers. There's 4 and there's 5. So I need to spread those out evenly so that I'm going to end up with 3 hours represented in each quadrant. So I'm going to put 4 closer to 3. And I'm going to put 5 closer to 6, like so. Again, we're just going to estimate. We're going to eyeball it. 4 o'clock is closer to 3 o'clock, and then 5 o'clock is closer to 6 o'clock, like that. So that's how we're going to divvy these up. Now I'm going to connect those to the other side, and that's going to give me 10 o'clock and 11 o'clock over here. So we're cutting this up into 12 pieces. We've got to cut each fourth into thirds. And we'll do the same thing over here. So I'm going to say 1 o'clock should be about here, and 2 o'clock should be about there. And I'm going to connect those to the other side of the circle to make 8 o'clock and 7 o'clock. Okay. It's a clock. So some of these angles we have already talked about. We've already talked about 0 and 180. And if we're starting from 3 o'clock over here, this angle straight up at 12 o'clock is, of course, it's still 90 degrees, right? And what's this angle straight down? 6 o'clock in this case? Yeah, it's 270. It's 180 plus another 90, 270. And if we make it all the way around, it's still 360. That's old news. Let's get some new news. So this first angle right here, between 3 o'clock and 2 o'clock, how many degrees is that going to be? What fraction of the entire circle is this? Yeah, it's 1/12 of the entire circle, right? So what's 1/12 of 360? 30. So we've cut the entire circle up into 12 pieces. Each one is 30 degrees. So this first angle is going to represent 30 degrees of rotation. And then we just keep counting by 30s as we go around. So 30, 60, we already have 90, 120, 150. If you're having trouble, just count by threes and add a 0 to the end. So there's 150, 180, 210, 240, 270, 300, 330, and after an entire circle, after 12 hours, we get to 360 degrees. So each hour on the clock is 30 degrees of rotation. So when we think about these 30-degree angles, it'll be helpful to imagine a clock. Okay. Now let's try to do the same thing in radians. Now, for radians, we want to figure out what fraction of pi each angle is. So we're going to look at half of a circle, because that's how much pi is. So what fraction of pi is each angle here? It's not a 12th of pi. 1, 2, 3, 4, 5, 6, right? This angle is 1/6 of pi. So we're going to call it pi over 6. 1/6 of pi. So instead of counting by fourths this time, we're going to be counting by sixths. So this is 1 out of 6. The next one would be 2 out of 6. But instead of writing 2 out of 6, that reduces to what? You're right, to 1/3. And then 3 out of 6 reduces to 1/2. 4 out of 6 also reduces. It's 2/3. 5 out of 6 doesn't reduce. 6 out of 6 reduces to 1. 7 out of 6 doesn't reduce. 8 out of 6, that's 4/3. 9 out of 6, that's one that we already have. That reduces to 3/2. 10 out of 6, also going to reduce to 5/3. 11/6. And finally, we get to 12 pi over 6 when we've made a complete circle, which is exactly 2 pi. Okay. So, our goal here is to be able to find these angles not by looking at this picture, but just by knowing how to count. So what I'm going to have you do in the homework is try and draw these angles without just looking at this picture, but by counting. So you want to be able to do this using some intuition. So if I ask you to draw, let's say, 120 degrees, should I be counting by 30s or by 60s to get to 120? Sorry, by 30s or by 45s? Which would make more sense? Should I think about the clock by 30s, or should I think about counting by 45s like this? Yeah, let me think about the clock. So if I count by 30s, there's 30, 60, and 90 right there. Then 120 would be 30 degrees past that. So 30, 60, 90, 120. So there's 120 degrees. It's that angle right there. Okay, so I have some practice problems up for you. And again, we just need to get an intuitive sense of how big angles are. Because angles are going to come up a lot in trigonometry. Like every time we work the problem. Okay,